Hello everyone. My name is Elliot Brendel and I will present you our work with Julien Alexandre Di Sandretto and Alexandre Chaputo about robust motion planning based on sliding horizon and validated simulation. At first, let's assume we have an autonomous robot, which is a critical system. So, for example, it's very expensive, or it has to perform a dangerous task. So it's subjected to a dynamics controlled by parameters. So here y is the state vector and u is the parameters. And so we want the robot to perform its task and to move in an optimal and safe trajectory. And we also assume that it discovers its environment gradually. So the robot doesn't know the entire map. So let's say a few words about validated simulation. So it's the interval counterpart of numerical integration methods. So basically it provides a list of boxes ensuring that they contain the solution of the ODE. It's the way to solve the dynamics of the robot that we choose, because the system is assumed critical and its safety must be guaranteed. Yes. Then a few words about sliding horizon. So the idea is to simulate the solution of the ODE on a large time span t, which is the prediction period, and then the robots will only move by a smaller time period t prime, which is the sliding period, and then starting from t prime we repeat these steps. So it's a way to model that the robot discovers its environment gradually, and it's also safer to move by smaller step than what we see. So our problem can be formalized like this. So we want to find a trajectory y, which is a solution of the dynamics, which minimizes the cost g, and which satisfies constraint h. So, for example, the constraint will be from the safety, and the cost will be from the task. So our approach combines validated simulation and the sliding horizon. So first, we assume that we have a discretization of our parameters. So, for example, here there's 4 value of the parameter u. And then in a loop, we performed sliding horizon algorithm, and we use validated simulation to find the trajectory from the ODE. So in this loop, we will test if each trajectory satisfies the constraint and minimizes the cost. So, for example, at first there's a trajectory u1. So here the robot meets an obstacle, so it's not a validated trajectory. And then we test u2, so we can keep it, and we keep its cost. And then u3 and u4 that satisfy the constraint, but that have a bigger cost than u2. So we keep u2, and at t prime we start again until we reach a number of steps defined by the user, or until there's no feasible solution that can be found. So we provide an improvement of this approach using set membership. So instead of testing each value of the parameter, we can test after finding a valid trajectory U2. We can test the whole interval U3, U4. And if the resulting cost cannot be better than the cost resulting from U2, we can directly throw away U3 and U4. So we applied this approach to an autonomous underwater vehicle, which is subjected to this ODE, where x, y, z are the coordinates, psi, theta, phi are the layer angles. There's a two-dimensional parameter u1 and u2, for example, a steering angle of the rudder, and v is the cruise speed, so we assume it's constant. So the problem for the AUV can be translated like this. So here we want to be the closest to the seabed, so we minimize the depth z. It has to be a solution of the ODE, of course. And as constraint, we consider that because of safety, we want to be at least at a distance d min from the seabed. And we want also, because of the sensors, to be at least close to the seabed with a distance d max. And we also bounded the pitch to limit the dive angle. Then we consider a particular mission. So here we want the AUV to go forward. So we impose x end bigger than x init. And we also bounded phi and psi to limit for the AUV to not capsize and to go in a quite straight way. So for our experiments, we consider the following seabed. So we turned it 4 times of 90 degrees. So there are hills, there are pits, and we want the AUV to be to follow the depth variations, starting from different sides. So for the experiments, we assume that the AUV has to be at least 1 meter far from the seabed for its safety, so that's d min. Its sensor has a 10-meter range, so that's d max. Its cruise speed is 0.1, that's v. Its initial depth is at minus 92 meters, so that's the initial state. And the two radars have a 10-value resolution of their steering angle. That's the discretization of our parameters. It changes these angles with a period of 15 seconds. So that's our sliding period, T prime. The AUV knows its environment 30 seconds before reaching it. So that's our prediction period, T. And each experiment is stopped after 35 moves of the radar, so that our number of states step. So for the implementation, we choose to implement the approach with the Dynavex framework. So it provides a validated simulation procedure based on Runge-Kutta methods. And it also provides some differential constraint programming facilities. So every simulation has been computed using a Hund's method and 10-4 precision, which is a good trade-off between speed and precision of the results. And the improvement using set membership we discussed previously provided a 10% reduction of the simulation time. So we realized the experiments in 3D and then we projected it in 2D because it's easier to see. So for the first seabed, we start quite high, and in front of us there is some hills and a valley. So because we want to be always to minimize the depth. The AUV will pass by the valley, and then it succeeds in passing the other hills in front of him. For the second experiment, we start upon a hill, and to the right there is a very deep pit, but the AUV succeeds in diving and then in straightening its trajectory. So without the sliding horizon approach, maybe it will not dive strongly and then hit the ground because it wouldn't have anticipate the hill after the pit. The third seabed, we start upon a very high hill, and then we reach. So we dive, keeping a 1 meter distance between the seabed, and then we reach the flat part of the seabed, and we succeed in leveling off. So as you can see, there are some oscillations once we reach the flat part of the seabed. That's because the only constraint here is x end bigger than x init. So the AUV keeps moving forward, but yeah, it oscillates. And for the last seabed, it's a failure because the AUV dived too strongly and then hit the seabed. So so we provided two solutions for this experiment. So the first one could be obtained by increasing the prediction period t, so the AUV see further, and decreasing sliding period t prime, so we move by smaller step. So it increases the computation time, but as you can see, it works. And the other solution is to add a constraint to the problem. So here we bounded the diving speed, and we find another trajectory, which is a solution. So as a conclusion, we proposed a validated algorithm which solves a motion planning problem considering constraints and constant states. Our approach showed its efficiency in an application of motion planning for an AUV. We proposed also an improvement exploiting set membership to avoid some tests on inputs, and it reduces significantly the number of simulations. And the presented approach can, in some cases, fail because of its dependency to many parameters that the user has to calibrate. As future work, we can think about a procedure to dynamically choose the parameters, such as the prediction or the sliding periods, or additional constraint on the system behavior. We could also test our approach on new examples of application, so with different system constraints and costs. Or we could also consider time-varying obstacles and seabed. Thank you for your attention.
We are quite in advance, so we have 5 or 10 minutes for question. You have some question?
So maybe I missed something, but in the how is designed the control input? Is there a priori parameterized form of the control input, or is it how do you define your candidate trajectories?
Right. The control input depends on the considered problem.
Yeah, but
So
in that case,
in that case,
how do you define your candidate trajectory?
Here. So the control inputs are here. U1 and U2. Yeah.
But I mean,
Yeah.
I mean in terms of receiving or horizon, you
Yeah.
And how do you design those possible trajectories?
Okay, so for example, if here it's an angle and I know it's, I don't know, maybe between minus pi and pi, well, I will discretize this interval with the resolution that I know my radar can have. So if it can move some, yeah. Yeah.
Yes. So I did not understand the oscillation you got in your previous.
Yeah.
Yes, here.
Yeah.
So at the beginning is at the top, no?
Yeah.
So in red it is a trajectory.
Yeah.
So at the beginning it is where is the start?
Here. Yeah.
Okay. So and the oscillation is due to what?
It's only because
in the horizontal plane,
yeah.
you said, or
Yes.
because there are
Yeah.
also some small oscillation in the vertical plane, but you are talking about the trajectory on
Yes,
the
Yeah, yeah.
horizontal plane.
It's
Here?
Yes,
Yeah.
here.
That's because there are not the only constraint once we reach the flat part of the seabed is this one, its end bigger than its init. So so the AUV keeps moving forward, but we didn't care if it was straight or we could oscillate. That's not.
Okay, so
Yeah. We could add constraint to tell the AUV to be.
Okay. So there is no specific reason for
No.
this. Okay. And the same the pitch theta is when you say it's not absolute value, it's
No, it's not absolutely. It's only because of the dive.
so
We don't want the AUV to dive too strongly. But
okay, so we can go like this.
yeah, but because we minimizes the depth, it will not
Okay.
go like this.
Okay, no problem. Thank you.
Some more questions?
Can you go back to slide 20 or something like that? Yeah. What's the reason for the AUV to choose to go that direction or the other one? Meaning going down to the, you have another
You
meaning
mean,
there.
yeah.
It's only the initial conditions or it's something?
It's because of what the AUV know about its environment because of our prediction period. So I think the AUV doesn't see this fit when he starts. So, but he knows that there's a pit here. So he will move with little steps by here, and so he will completely avoid the pits on the right. The AUV doesn't know the entire map, so maybe if we increase
another direction,
if we increase the prediction period, maybe the AUV will consider this pit and will go that way.
Then maybe it becomes unstable.
Yeah, but if there's no feasible solution, it will not.
I'm trying to relate what you say to the optimization problem you presented.
Mm-hmm.
The optimization problem has a better solution
Yeah.
on the other
Yeah.
side.
Okay. Yeah.
So all this is linked to the sliding window. Is what you're
Yes.
saying.
Yes.
Okay. Thank you.
One question more?
Just concerning your constraint that what Luke just asked with the theta. You have theta less than minus theta, no, less than 0.8.
Yeah.
I assume you need a lower bound because your trajectory could be something like a looping. Otherwise, you could go around in a circle and then go straight down vertically.
Yes, maybe.
Yes, but probably
Yeah,
you
but-
will have to cross a singularity in the
Maybe
video state model.
Maybe I don't know. We didn't encounter that
Then
case,
you
but
must need a limitation to prevent the singularity.
Yes. Yes, because
But-
in the state model, when cos theta, you divide by cos theta, so if
yeah. But well, that's not a problem. We can bound.
so maybe you should
The,
avoid this
yeah.
singularity.
Yes.
Well, we can add this constraint. That's not a problem.
No more question? I have one question about the prediction time. We talked several times about that. Or you said that you have a fixed prediction time. You try to increase this prediction time in some scenario to see if by doing that you are able to avoid tricky situation and bad solution, collision. Did you try to apply adaptive process to compute or to fix in line the prediction time, or it's always something fixed from the beginning until the end?
Yeah, in these experiments, it's always fixed from the beginning to the end. But yeah, that's an idea of future work.
Because according where you are on the scenario,
Yeah.
if it is at the beginning, or if you are close to the terrain, if
Yeah.
you know that the terrain is rough or flat,
Mhm.
maybe it could be interesting to dynamically
Yeah.
increase the prediction time. And then after, think about how to relate this prediction time to constraint, to more mathematical stuff. Okay. Some more questions or comments? Otherwise, it's time to close this session and to move to the next one. Thank you again.